In this module, we will start with the introduction to the applications of probability theory, and we will do a review of set theory. So probability theory finds a variety of applications in several engineering domains, some of which I've listed here. So for example, we make heavy use of probability in designing reliable wireless systems and in wireless communications. It's an indispensable tool in signal processing, how to retrieve information, how to compress information, and understanding statistical properties of objects that we transmit using our devices, phones, tablets, and so on. It's a useful tool for doing statistical inference and making decisions under uncertainty. And no course would be complete without mentioning AI and machine learning, which is the hot topic these days. And the list keeps going on and on. So I'll just stop by saying medical diagnosis and healthcare also involves tools from probability theory. So for the scope of this course, we'll focus on something called the axiomatic approach to probability. So let me just mention that. So we will focus on an axiomatic approach to probability theory. So what do I mean by an axiomatic approach? An axiomatic approach essentially means the following, that instead of thinking of it in a philosophical manner, we will define some axioms. And some axioms, so think of axioms as some, set of rules. And whenever we deal with events and assign probabilities to them, that we will always follow those rules. And there'll be a simple set of rules, and then our mathematical model for a setup where we reason and argue about probability will always have to follow those rules. Now, the axiomatic approach relies on set theory. So in this module, what we're going to do a little bit of review of basic set theory, which hopefully everybody has seen, but nonetheless, it's good to just revise the concepts and get familiar with the terminology. So that's what we're going to do next. So we'll start with a review of set theory. So let's start with what is a set. So a set, and this symbol, if you have not seen this, this means set is defined as a collection of elements, as simple as that. Okay. So for example, if I take a set A, and I'm going to always describe a set with curly brackets, and the elements inside the curly brackets will be the elements of that set. Okay. So for example, if I say two letters H and T, so typically in probability, H stands for heads and T stands for tails. So if you flip a coin, and there are two possible outcomes, heads and tails. So this is a set which has two elements in it. Another example is, a collection of elements. So for example, 13, 14, 15 is a set of three elements. So hopefully this is clear. We also define something called an empty set or a null set. So an empty or null set is defined as this object. So this object essentially contains no element. Okay, that's why it's called the empty set. It contains no element. Okay. The second thing I want you to remember or recall from your past is what is the total number of subsets we can form using n elements. It turns out this number is 2 raised to power n. Okay. So I'll give you an example. Now, suppose we take a set S, which is 1, 2, and 3. Okay, and I want to list all possible subsets that you can form from these three elements. So list all possible subsets of S, which is 1, 2, 3. So of course you will say, well, I can pick an empty set. I pick nothing. Or I can pick one element. So I'll get these sets 1, sets 2, and sets 3 containing single elements. So this is one set, which is the null set. These are 3 sets containing individual elements. Then you could pick any 2 elements out of the set, 1 and 2, 1 and 3, and 2 and 3. And there are 3 such sets. And then you can, of course, take all the elements, and there is one such set. Okay, so if I add up the total number of such sets, so I get 1 plus 3 plus 3 plus 1. How many sets do I have? Which is 8, which is 2 raised to power 3. Okay, n was 3, so n was 3 elements, and the number of subsets for this example is 2 raised to power 3, which is 8. Okay. Now, this is something you probably know. How to compute this in general. So in general, this formula is nothing but a simple application of the binomial theorem. So the number of subsets is n choose 0 plus n choose 1 plus all the way till n choose n. And it turns out this is equal to 2 raised to power n. Okay. Where does this come from? I'm going to mention things on the side in this purple box in my modules. So I'm going to write binomial theorem here. So try to check yourself about binomial theorem. So binomial theorem says that if I have two numbers, x plus y, if I look at x plus y raised to power n, we can write this as n choose I, x raised to power I, y raised to power n minus I going from 0 to n. So if you believe that binomial theorem is true, you can prove that the above sum, which is this guy, can follow by setting. So if we set x equal to 1 and y is equal to 1, the left-hand side will be 2 raised to power n, and this will be equal to the right-hand side, which will be, so if x is 1, y is 1, these terms become 1. I get n choose 0 plus n choose 1 all the way till n choose n. So essentially, it's the sum of all binomial coefficients, n choose I going from 1 till n, 0 till n. Okay. And that's how you get this count of the total number of subsets of a set containing n elements. Okay. Let's move on to review some other basic properties. So once you know what is a set, you can do operations on a set. So let's look at some set operations. So you will see this kind of notation: B is contained in A. So what this statement means is, this means that B is a subset of the set A. Okay. Once we have defined this notation of inclusivity of subset, then we can think about deriving some additional properties from it. So for example, there's something called transitivity. It says that if C is contained in B, or C is a subset of B, and B is a subset of A, then this statement implies that C is contained in A. Okay. So think of it like this. So I have a set B, and C is contained within A, and B is contained within A, then of course C is contained within A. That's what this transitivity is. Okay. We can also talk about when are two sets equal. So equality. So we say two sets are equal with 3 lines. So this is set equality sign. if and only if, and we'll use a shorthand IFF throughout the course. If and only if I say IFF, that will stand for if and only if A is contained in B and B is contained in A. Okay, so hopefully this is clear. Once we have defined this thing, then we can talk about union and intersection of the sets. So we can define union of sets. So for example, union of the set, if I have two sets, A union B will denote the union of the sets. So for example, if I have a set A is 1, 3, and say elements alpha, beta, whatever they mean at this point, and B is 3, alpha, and 7, then what is A union B? It is the set of all elements which are contained in either A or B. So I'm going to write 1, 3, 7, alpha, and beta. So this will represent the union. And then we can also write the intersection of sets, which is denoted by intersection. So for the above example, what is A intersection B, which contains elements which are in both the sets. So which elements are in both the sets? 3 is in both the sets, and alpha is in both the sets. Okay, perfect. We can also do some other interesting properties. I'm going to list a few of them. So for example, A union B is the same as B union A. Okay. What this means is the order in which you take the union doesn't matter. The result will still be the same. So this statement is also written in a formal way as a commutative operation. So which means that the operation of taking union is commutative. Okay. Another property we can easily derive is, say I have three sets and I look at A union B union C, which is the same as, so I do the following here. So on the left, I do find the union of A and B. After that, then I compute the resulting union of the new set and C. Okay. This will give me the same answer if I take the union of B and C first and then take the union with A. Okay. So this is called associativity property. Same thing for intersection. So A intersection B is the same as B intersection A, and intersection operation also satisfies this property that if I take A intersection B and then take it with C, it's the same as taking the intersection of B and C and then taking the intersection with A. Okay. Sounds good. Now, here's another interesting property that I'm going to put it in a red box because this is slightly more interesting and non-trivial, which is the following. So if I take a set A and look at the intersection with the union of two sets, say B and C, okay, then we can write this as taking the intersection of A with B and then taking the union with the intersection of A and C. Okay. So I'm going to just write an interesting property to remember. Okay. How do we prove this result? Proving this result is not hard. I'm going to sort of give you a Venn diagram way to prove this result. So think of it like this. So imagine I have the set B and I have a set C. Okay. So first let's try to understand what is the union of these sets. So the union of these sets is this guy, this stuff in teal. Okay. Now if you take a set A, so let's think about another set A. So I'm going to maybe draw that guy in a different color. Say this color. So suppose this is my set A. Okay. So what is the intersection of A with the union of B and C? It is this guy in pink. Hopefully everybody's okay with that. Right? So what the above result is saying is that this pink can be written as the union of two objects. It's this object, which is intersection of A with B, and the intersection and union with the intersection of A with C. So this common part, which is sitting in the center, is only counted once. Okay, and we take the union. Hopefully that is clear. So in some sense, you can view this as a Venn diagram interpretation of the above property. Okay. Okay, very good. Let's move on. There are a couple of more simple properties, and then we'll stop this module. The next thing I want to talk about is mutually exclusive sets or disjoint sets. So we say A and B are disjoint or mutually exclusive if the intersection is the empty set. Okay. What does this mean in a Venn diagram sense? So I have a set A and I have a set B. They have no intersection. Okay. So then this means they are disjoint. Okay. They have nothing in common. We can also generalize this definition from disjointness of two sets to three sets. Okay. So we can say A, B, and C are mutually disjoint or mutually exclusive if what properties hold? If A and B have no intersection and A and C have no intersection and C and B have no intersection. So visually this is what it means. So A sits like this, B sits like this, and C sits like this. Okay, so that's the way to think about it. Right? Simple enough. One more thing we can talk about is the complement of a set. Okay. So the complement of the set, you will see two types of notations in various textbooks and sources. So sometimes we will write A with a superscript C on top, or sometimes as A with a bar sitting on top. Both mean the same thing. So imagine, so how to define complement? To define the complement of a set, we have to define the space of all elements that we are considering. Okay. So suppose we define S as the space of all elements in consideration. Okay. Then if A, let's say, has some elements. So for example, suppose S is 1 till 10. So it has 10 elements in it. And A is 1, 2, and 3. Then what is the complement of A? The complement is everything which is not in A, but it is present in the space of all elements. Okay, so everything not in A. Okay, so what will it be? It will be 4, 5, 6, 7, 8, 9 till 10. Okay. So a complement has all elements in S which are not present in A. Okay, that's the complement. We can also write a complement in an interesting way in a shorthand manner. So the shorthand notation will be S, this slanted bar, A. So what is this operation? This is a set minus operation. All this operation does, it takes all elements of S and removes all elements from A, and the resulting thing is the complement of A. Okay, so this is something to remember, this notation. Okay. Now with this in mind, we can see a few things very easily. If I take A and take the union with A complement, what will I get? I will get back the space of all elements, right? Why is that? So imagine this is my S and A sits here. Okay. If this is A, suppose I shade it with this color, Then what is A complement? A complement is everything outside A, which is in S, right? So this green part is A complement. So if I take the union of A and A complement, what will I get back? I'll get back the space of all elements. Second property to remember is if I take the intersection of A and A complement, what will that be? Do they have anything in common? No. So this will be the empty set. Okay. If I take the complement of A and take the complement of its complement, what will I get back? I'll get back A. Okay. What's the complement of the space, the set of all elements? It's the empty set. What's the complement of the empty set? It's the space of all elements. Okay. So these are some simple properties of the set minus operation and complements and so on. These are what. Another interesting property to remember is that if I have two sets, B and A, and if suppose B is a subset of A, then A complement will be contained in B complement. Okay. So this is something you can check yourself, very easy to prove. I'm going to close this thing with two properties, namely De Morgan's laws. And I will not prove them, but I will ask you to prove yourself. Check and prove yourself, which are not too hard to prove. Other fall into properties that if I take the union of two sets, say A and B, and I look at their complement, the complement of the union, it can be written as the complement of A intersection with the complement of B. Okay, that's the first law. And the second property is if I take the intersection of A and B and look at the complement, it can be written as A complement union B complement. Okay. So these are two properties. See if you can try to convince yourself that these are correct. But I think this is a good exercise. So I encourage you to try this yourself. So we're going to stop this module here and resume in the next one. Thank you.